All right, these are the answers to page 193. The first four want us to match these with graphs. And the key is just to look and say, well, when we have a factor that's on the bottom that doesn't cancel, this creates a vertical asymptote. So this would be a vertical asymptote at x equal -3. So if I look at my options, the one that has a problem at -3 was D. That had the vertical asymptote. This has a vertical asymptote at +5. That was A. This one has a vertical asymptote at +4. That was C. And this one had a vertical asymptote at -4, and that appears to be B. So again, just looking at what the problems are. Now, not everything time you are in the bottom are you going to create a vertical asymptote. And 21 and the rest of these want us to declare where are our holes, vertical asymptotes, and then to talk about something called a horizontal asymptote. So we'll start with the vertical and horizontal asymptotes. First thing we have to do is factor. So this x squared minus 16 factors into x plus 4x minus 4. We're going to have an issue at -4 and an issue at 4. We can't equal either of those because they make the denominator 0. However, this x minus 4 does cancel. And when it cancels, it just means that it doesn't have a big impact on the shape of the graph. In other words, at x equal 4, there's going to be a little hole in the graph. All right? Just a tiny little hole. It's not going to disrupt very much, but we technically can't equal 4 because of it being in the denominator on the original function. Now, x equal -4, however, is a big problem. That's a big disruption. That's going to be a vertical asymptote. Okay? And so those are what we call discontinuities, the problems the graph's going to have. But they look very different depending on what happened there. Now, as far as a horizontal asymptote goes, what we're going to do is look at the nature of this. I have x to the first, I have x squared. X squared dominates x. So as x gets bigger and bigger, this is going to get much bigger than this is. And if the denominator is much bigger than the numerator, that means these are fractions with large denominators. That creates tinier and tinier and tinier numbers. We're going to have a horizontal asymptote at y equals 0. In other words, as the bigger x gets, the smaller those values get. We're heading off to a value of 0. Okay? Same thing here. If I factor this, x plus 3x minus 3, those cancel. So at x equal -3, we're going to have a hole in the graph. But at x equal +3, there's going to be a vertical asymptote. And again, the denominator x squared, much more significantly bigger than the top, so we'll have a horizontal asymptote at y equals 0. Anytime the degree of the denominator is bigger than the degree of the numerator, y equals 0. It's going to level off to 0 over time. This one here, if we factor the top, it's x plus 1, x minus 1. If we factor the bottom, it's x minus 3, x plus 1. All right, so we're going to have problems at 3 and -1. However, the x plus 1s do cancel. So at x equal -1, we're going to just have a little hole in the graph. At x equal 3, we'll have a vertical asymptote. Okay. At x equal 1, we're just going to have an intercept. That's okay. We can be 0 on the top. We just can't be 0 on the bottom. That's a big no-no. Now, as far as a horizontal asymptote, the degree on the top and the degree on the bottom are the same. So as x gets bigger, they're going to get bigger at the same kind of degree or rate. And so in a case like that, you look at the numbers in front of them and you say, well, this is 1 to 1. 1 divided by 1 is 1. That is what this is going to level off to then. Over time, the values of the top and bottom are going to pretty much equal each other, and we'll just have 1 then for our answer. For 24, if I factor the top, x plus 2x minus 2. Factor the bottom, x minus 2, x minus 1. Again, we're going to have problems at both of these, but the x minus 2 cancels. So at x equal 2, there's going to be a hole in the graph. At x equal 1, there's going to be a vertical asymptote. Okay. If I look at the original, x squared, same degree, same relative strength. 1 divided by 1 means our horizontal asymptote will be y equals 0, or y equal 1. I go to this one, factor the top, that's x minus 4x plus 1. Bottom factor is a little goofy. We got to include the 2 in when we do it, and should factor this way, 2x minus 1, x plus 1. The x plus 1's cancel, so at x equal negative 1, we'll have a hole in the graph. At x equal, and if you set this equal to 0, add 1 divided by 2, you get 1/2. 1/2 is where our issue is going to be, and that's going to be a vertical asymptote because it didn't cancel. Okay. Now, as far as a horizontal asymptote goes, look at again, x squared, same strength, but this time, if you take coefficients, 1 divided by 2, over time, this is going to level off at a value of 1/2. So again, if the degrees are the same, divide top and bottom, whatever those coefficients are, and that's what your horizontal asymptote is going to be. For this one here, if I factor the top into x plus 3, the bottom into x plus 3x minus 2, my x plus 3's cancel, so x equal negative 3 will be a hole in the graph. X equal 2 will be a vertical asymptote. Okay. And our degrees were the same, 1 divided by 1, that means our horizontal asymptote will be y equal 1. All right, last one here, if we factor the bottom, x plus 4x minus 3, you can see the x plus 4's cancel, so at x equal negative 4, we'll have a hole in the graph. At x equal 3, we'll have a vertical asymptote, okay? 5x on the top is not as significant as x squared. The bottom will dominate, and so our horizontal asymptote will be y equals 0. These will get smaller and smaller and smaller over time, eventually equaling almost 0.